Our goal is to develop a set of differential equations that tell us how the orbital elements of a pure two-body orbit change in time in response to some specific perturbing force, F. It is often most convenient to express F in components of a rotating frame that is moving along the orbit. And this is especially true in cases where F represents the perturbations due to spacecraft control, due to a propulsion system on the spacecraft. But there's many other naturally occurring perturbing forces that can also be easily expressed in this kind of frame. We have already defined a frame of this type multiple times, and this B frame, as shown here, is effectively equivalent to our Hill frame, or Euler-Hill frame. Its first component direction, E hat r, points along the orbital radius vector rp-rel O, where the central body is at O. Its second component is in the parafocal frame of the orbit, orthogonal to E hat r, which we call E hat theta, and its third component is orthogonal to the parafocal plane of the orbit, and therefore the E hat z direction is equivalent to the angular momentum direction of the orbit. Anytime we work in a rotating frame, we need to know its angular velocity in the relevant inertial frame. In this case, the angular velocity of B and I is given by the rates of change of the Euler angles defining the orientation of the parafocal frame of this orbit in this inertial frame. So you will recall that in order to go from the inertial frame to the parafocal frame of a specific two-body orbit, we first take a capital omega rotation about the E3 direction. And so the associated angular velocity is omega dot about E hat 3. We then take an inclination rotation about the line of nodes. And so the angular velocity associated with that rotation is I dot in the n hat direction. And finally, we take a lowercase omega rotation, argument of periapsis, about the angular momentum direction. But in this case, our B frame is also moving along with the orbital radius vector. And so the total angle between the line of nodes and the orbital radius vector is the sum of the argument of periapsis and the true anomaly, and is given by the argument of latitude, theta, which we have previously defined as omega plus nu. And so the third component of the angular velocity is theta dot about the h hat direction. If we write out the relevant direction cosine matrices and convert each of these into components in the B frame, or equivalently the Hill frame, then we get this component expression for I omega B. By inspection, we can write the components of the radius vector r, which is equivalent to rp-rel O in this diagram, as just the magnitude of the orbital radius in the ER direction in B frame components. And we know that we can write the velocity in B frame components as just two components Vr and V theta in the ER E theta direction, because the velocity must lie instantaneously in the parafocal plane. So this is a key observation about what is happening here. Even though we have a specific perturbing force acting on our object, we can, for every instant in time, define a parafocal plane in which the orbital motion lies. And so we fully expect time evolution of this plane, which means that we expect time evolution of these various angles, which ordinarily in the regular two-body problem would have zero time derivatives. So this is what the specific force is doing to our system. It is allowing for a non-zero capital omega dot and a non-zero I dot, and so on. The force components will be written as F sub r, F sub theta, and F sub h in B frame components corresponding to the ER, E theta, and H hat directions. The angular momentum in the B frame is always given as 0, 0, and its magnitude in the H hat direction. And finally, the eccentricity vector is given by the eccentricity magnitude times cosine nu in the ER direction, and negative the eccentricity magnitude times sine nu in the E theta direction, again with the eccentricity vector always lying in that instantaneous parafocal plane of the orbit. We now apply the transport equation to the time derivative of the specific angular momentum of our orbit, which tells us that the body frame derivative of h plus the angular velocity of b and I crossed with h equals our previous result. The time derivative of h in the presence of a specific perturbing force is the orbital radius crossed with that specific perturbing force. And if we input the component definitions in the B frame, we get this expression here. Similarly, we can apply the transport equation to the time derivative in the inertial frame of the eccentricity vector, set it equal to our previous result, apply the component forms of all the various relevant vectors, and get this set of scalar equations. And you will notice that in these equations, we have terms of capital omega dot and I dot and theta dot and lowercase omega dot and E dot, which means that we should be able to algebraically solve these for differential equations in each of these Keplerian orbital elements. It is absolutely not worth our time to do this by hand. Instead, let's turn to a computer. We are once again going to demonstrate this symbolic manipulation using the SymPy package in Python. You can get absolutely equivalent results with any number of symbolic math tools in any number of languages. So here we have the same diagram. And here we're going to set up our system. To set up our symbolic computation, we first need to define all of the relevant variables. And we're going to do this in 2 steps. We're going to define all the things that we know to be strictly positive quantities as such, and then everything else which is a real value, but not necessarily positive, just as real values. The reason why we're doing this is that we want to do everything we can to help the symbolic package do algebraic simplifications, and noting which things are strictly positive and which things are just real, and which things cannot be said to be real or positive is an important part of that. So the semi-major axis, the mean motion, the gravitational parameter, the magnitudes of the orbital radius vector, eccentricity vector, and specific angular momentum, these are all things that are strictly positive. Everything else, the Euler angles, their time derivatives, the components of our specific perturbing force, and potentially the true anomaly, these are all things that are positive or negative, but strictly real quantities. We next define the rotation matrices associated with the mapping between the inertial frame and the parafocal frame. That is a capital omega rotation about the 3rd unit axis, an I rotation about the 1st unit direction, and a theta rotation about the 3rd unit direction. And the angular velocity of B and I, as we've previously stated, is capital omega dot in the E3 hat direction, I dot in the N hat direction, and theta dot in the H hat direction. So this is how we got that component representation that was given in the slide. We rotate the omega dot term by the 2nd rotation matrix and the 3rd rotation matrix into the B frame. The I dot is just rotated by the 3rd rotation matrix into the B frame, and the theta dot is already in the B frame. And this is the result. Next, we apply the transport equation. So we define our specific angular momentum vector. We differentiate it, we define our position vector and our force vector, and then we add the cross product, and then we solve for the various terms H dot, capital omega dot, and I dot. And here we go. So this first expression is sufficient to get us expressions for the time rate of change of the inclination and the time rate of change of the longitude of the ascending node of the orbit, as well as the time rate of change of the specific angular momentum magnitude. We do the exact same thing with our differential equation for the eccentricity vector. And in this case, we are going to do a few substitutions in order to allow, again, the symbolic solver to do its job. But what we're looking for here at the end are solutions for the eccentricity derivative, eccentricity magnitude derivative, and the derivative of the argument of periapsis. And we get these forms, which are slightly more horrifying than these simple expressions, but are still very tractable. And that's really all there is to this. Just by using the 2 differential equations that we previously derived for the specific angular momentum vector and the eccentricity vector, and plugging in component definitions of all of the relevant vectors in those expressions in the rotating body frame components, we instantaneously get differential equations for all of the orbital elements. Or almost all of the orbital elements. You'll notice that the semi-major axis was not actually explicitly included in any of those component definitions. However, we can solve for it because we have everything else. We know that H, the specific angular momentum magnitude, is equal to the square root of mu A times quantity 1 minus E squared, which means that the semi-major axis is equal to H squared divided by the gravitational parameter times quantity 1 minus E squared. We can differentiate this in time and write that is A dot is equal to 2E E dot H squared over mu times 1 minus E squared quantity squared plus 2H H dot over mu times 1 minus E squared. We've already derived expressions for E dot and H dot. We simply plug those into this expression, and we get another equation for A dot as a function of our perturbing force components. We can squeeze out one final result from the system of equations by considering the angular velocity component that is normal to the orbital plane. That is, I omega b dotted in the h hat or EZ direction. So this will be the third component of our angular velocity matrix in B-frame components. And if you stare at the geometry of this, we can see that it will be given by the orbital radius crossed with the orbital velocity divided by the orbital radius squared, which in, again, our body frame components boils down to r v theta, the e theta component of the velocity, over r squared, which is just v theta over r. The magnitude of the specific angular momentum is always given by r v theta. And you can check this by carrying out the cross product in the component form of r and v vectors. And so this entire expression is given by h over r squared, which means that we have an equation of constraint where the third component of that angular velocity in B-frame components, omega dot cosine I plus theta dot, must be equal to h over r squared. So these are Gauss's perturbation equations, and they are an incredibly powerful tool for studying the effects of specific perturbing forces as given in components of a frame rotating with the orbit on the orbital elements of that two-body orbit. They are most useful for getting deep intuitive understanding of what's happening when they cause these terms to vary relatively slowly in time. If the orbital evolution of any of these terms is incredibly fast, if, for example, your perturbing forces are driving E from a bounded value of less than 1 to a value that is much greater than 1 very quickly within the span of a single orbit, well, you're talking about transforming a closed orbit into an open orbit. And so this kind of perturbation description is not truly accurate because at that point, you're not really perturbing the orbit, you're just massively changing it. So the real utility of this is to study gradual changes and bounded changes. And there's a lot that can be gleaned just by inspection of these. You will notice that some of these expressions are functions of a single component of the perturbing force only. For example, the evolution of the inclination is a function of the h hat direction of the perturbing force. Similarly, the longitude of the ascending node evolution is also only a function of f sub h. The evolution of the angular momentum magnitude is a function of f sub theta only. What that means is that if you know the form of your specific perturbing force, and it has no components in either the h direction or the e theta direction, then you know instantaneously that these terms will be zero. The evolution of the eccentricity magnitude is a function of both the e theta direction component and the er direction component of your perturbing force. So if your perturbing force is acting only orthogonal to your orbital plane for all time, then you expect no evolution in the eccentricity magnitude. The evolution of the argument of periapsis is a function of all three components. So the argument of periapsis will always be changing for any specific perturbing force. And the semi-major axis, much like the eccentricity, will only evolve if the perturbing force acts in anywhere inside the parafocal plane of the orbit. There are literally dozens of different forms of these equations out there in the literature and many different methods for deriving them. They all say exactly the same thing, but they might have different simplifications or algebraic substitutions being made. Just to give you a sampling, here are two other sets of Gauss's perturbation equations, one drawn from Batten's book and one drawn from Velato's book. In both these cases, the authors use P for the semiparameter. Batten uses F for the true anomaly. Batten uses A sub dr, A sub d theta, and A sub dh for the components of the specific force, A for accelerations, since these are equivalently accelerations. And Velato uses just capital F, R, S, W for our F sub r, F theta, and FH components. However, when you've mentally made these substitutions, and a few others based on the known relationships between our orbital elements, then you get exactly the same result as on the previous slide.